Okay, your equation can either be written as y equals the sine of x. It could also be written in function notation. So f of x, but let's use theta instead of x, since theta is the variable used very frequently with trig functions. So those mean the same thing. Okay, y equals sine of x, f of theta equals sine of theta. They're going to produce the same graph. Okay, it's just different ways of looking at it. So we will pull out Desmos tomorrow, but for right now, just look at what I got up here. So I've got sine and I've got cosine hidden right now. We're just looking at the graph of sine. Now, one thing to mention, when you open up Desmos on the exam, just like it is on the regular calculator, you're going to be counting by ones, and the default for this is actually degrees. It's the opposite of your calculator. So you need to change it to radians. Look how the graph is going to change when I click on radians. Okay, this is what the graph actually looks like. Now, this scale is not the same as the scale on our paper, right? If you look at the scale on your paper, it marks it off every pi over 2 units. If you go to the wrench up here in the corner, and on your x-axis, the step, you can change that to, you just type pi for pi over 2, and it will change the scale to what it is there on the graph that you're looking at. Now, it may be different on the graph that they give you on the exam. You just change it to whatever they have, pi over 4, pi, that's where you change that number. Okay, so let's put a little bit of this graph on your paper. Notice I can zoom out, and this pattern continues repeating itself. As far as I zoom out, it's still the same pattern over and over and over and over again. This is something that we call a periodic function because it has a pattern that repeats. So let's see here. On the graph that we're looking at, we don't go that far. The first point, the easiest point, I think, is 0, 0. Okay, it clearly goes through the origin. At pi over 2, the y value is 1. At pi, so pi over 2, 1 produces that point. At pi, the y value is 0. In the table there, we've got negative pi over 2. If we find negative pi over 2 on our graph, its y value is negative 1. So negative pi over 2, negative 1. Now, that's all that's in the table, but we can add as many points as we need to based on what we see in the graph. And then we don't want to connect these with straight lines. Clearly looking at the graph there, this is a curve. These are not linear pieces. They do have a curve to them. Okay, now that is just a small snapshot of the sine function. I already showed you that if we zoom out, it keeps going on and on and on forever. So that leads us to talk about the domain. Okay, remember, domain refers to the x values of our function. Anytime that we're trying to determine what the domain is, x values, we're looking left and right. So if we go to the left side of our graph, we are saying, is there a starting point to our graph? Is there a place where our function starts? And the answer to that question is no. It continues on for forever. So if there's no starting point, is there an ending point? Does it end over here to the right? I'm all the way out here at 60 pi right now, and obviously it's continuing on. The other question we ask ourselves, are there any breaks in the graph? Are there any vertical asymptotes? Are there any places where the function just jumps from one place to another? The answer to none of those questions is yes. So the domain, so the domain is all real numbers. Or the notation, if you recall, for that is negative infinity to positive infinity. X can be anything, and it'll give you an answer. It will produce the graph. The range are our y values. So we go bottom to top. If we're looking at our graph here, we don't have anything until we get to negative 1. We have a minimum value. And then our graph stops at +1. It does not go past +1. So that is one way to express that answer. -1 is less than or equal to y, which is less than or equal to 1. Or in interval notation, remember we use the square brackets when it's equal to. So we would write that square bracket, -1, +1, close the square bracket. Okay, so again, that applies to any function. When you're trying to determine domain and range, that method works. Domain, look left to right. Range, look bottom to top. That will allow you to figure out the domain and range of any function. Okay, since the domain is all real numbers, then this is what we consider a continuous function. Another way to look at it is if something goes on continually, it never ends, it doesn't have a break. This graph never ends, it doesn't have a break. We could trace it with our pencil and never pick up our pencil, so this is a continuous function. Okay, even, odd, and neither. We talked about this with some other functions. Let's apply it to this idea. If you will recall, even functions are symmetric about the y-axis. So that means that the y-axis cuts this in half and the left side is a reflection of the right side. Is that true about this graph? No. Okay, so it's not even. Odd functions have rotational symmetry, meaning if we took this and we flipped it upside down, it would look exactly the same. I don't know about you, I have a hard time visualizing that. So instead of looking at the symmetry, I look at the table. Remember, in the table, if you want the table in Desmos, you go over here, you click the little wheel, and you can click Convert to a Table. What we're looking for in the table is that opposite x values, so for example, -2, +2, either have the same y values. If they have the same y values, then that's even. If they have the same number but opposite signs, like we do here, that is odd. Okay, we can see that at -2 and +2. We can also see it at -1 and +1. They have the same numbers, but one is negative and one is positive. So that is an example of an odd function. If it were neither, these numbers would not be the same. Okay, we would not have the same value at -2 and +2, nor would one of them be negative and one of them, well, the negative and positive might be true, but they would be completely different numbers. Okay, so sine is an odd function because opposite x values have opposite y values. All right, local maximums and local minimums. Now, hopefully this idea makes sense to you. If this graph continues on for forever and it just keeps repeating the pattern, there are technically infinitely many maximums and minimums. We could list these all day long. We could list them until exams. We could list the maximums and minimums, but let's just list the ones that we can see here on the graph. So in terms of maximums, we can see a maximum at pi/2, 1. In terms of minimums, we've got a minimum at -pi/2, -1, and at 3pi/2, -1. But again, that's not all of them. That's just the ones that I can see on this little snapshot of the sine function that we graphed. All right, increasing and decreasing. Let's remind ourselves of that. We always move left to right. So as we move left to right, we are observing whether our graph is going up or going down. So again, just on this snapshot, this is not the only place that this is increasing or decreasing, but just based on the graph that we have, this function starts by decreasing. Our starting point was -pi, and it stops at -pi/2. Remember, we use the x values for this. Then it goes up from -pi/2, and it stops that at +pi/2. Then it decreases again from pi/2 to 3 pi over 2. And then it increases again from 3 pi over 2 to 2 pi. Now, technically, it does not stop increasing at 2 pi. It's going to continue until 5 pi over 2. But again, we're just looking at this little snapshot. There's more intervals of increasing and decreasing, and these are not complete, but that's what we're looking at right now. All right, let's talk about x-intercepts and y-intercepts. X-intercepts, obviously we have infinitely many of these as well. It is going to cross the x-axis many times, but let's look at the ones that we can see. We can see at negative pi 0, 0, 0, positive pi 0, and 2 pi 0. Notice those are all multiples of pi, by the way. Now, there are not infinitely many y-intercepts. It only crosses the y-axis once, and that is at 0, 0. Now, last thing that's review here is in behavior. Okay, so in behavior means our ends, so the far left and the far right, what y value, we're looking for the y value that we are approaching. So if we look at the far left side of this graph, the far right side of this graph, are we headed to one specific y value? Let me go back to this one. If I zoom out a little bit, if I go over here to the left as far as I can go, am I headed to one specific y value? No. What's happening? I'm continuously bouncing between -1 and +1. Most graphs that we've looked at, let me just throw up a couple of examples here. Let's talk about e to the x. Okay, e to the x, let me hide the trig function for a second. Okay, e to the x, if I'm talking in behavior, this left side of my graph is leveling off at 0. The right side of my graph is going to positive infinity. So that's what we're talking about with in behavior. This trig function is not behaving that way. It is bouncing in between. So the word that we use for that is it oscillates. So it has no in behavior. Well, the in behavior is described as oscillating. Okay, it bounces between y equals -1 and y equals +1. Okay, so the in behavior here is oscillating. It's bouncing between those values. It is not headed towards one specific y value or headed towards an infinity. It's just going back and forth. Okay, so that's all. Really, it's a review. We just applied that to the sine function. Now, here are some specific value or vocabulary words that will be used in reference to trig functions. The first one is called the period or the cycle length. I mentioned when we first looked at this graph that there's a pattern that repeats over and over and over again. So let me zoom back in here for a second. Pick a starting point. Obviously, the easiest one would be to start at the origin. You've got to complete the entire pattern before you start over again. So our pattern ends at 2 pi. It started at 0, it ends at 2 pi. So that is what we refer to as the period or cycle length. So the standard is 2 pi. Now I say standard because it's not always 2 pi. It changes, okay, just like with all of our other functions where we can add and subtract and multiply, we're getting ready to look at that with our sine and cosine functions as well. So the standard is 2 pi. We'll look at how it changes here in a minute. Okay, the midline. The midline is a horizontal line that cuts the graph in half. It's not a true line, because if you flip the bottom part up to the top part, it doesn't completely overlap, but it does make it symmetric. So again, this is also a standard. This can change. But if we look at our trig function here, what is right in the middle? What would be a horizontal line that would cut this in half? Well, that would be the x-axis, right? The x-axis runs right through the middle of this function. So the standard is y equals 0, which is, of course, the x-axis. Okay, and then finally the amplitude. The amplitude is the distance from the midline to a maximum or a minimum. It should be the same. If the midline is right in the middle, then that distance to the top or that distance to the bottom should be the same, right? So our standard if we go from the middle, y equals 0, to the maximum is 1. That distance is 1. That's the amplitude. We could also look over here from 0 to the minimum, -1. So either way, that distance is 1. Amplitude is always positive. Okay, amplitude is always positive. It doesn't matter whether you go up or down to get to it. It's a distance, so distances are always positive. Any questions about the review or the new stuff? Okay. No, I don't normally talk this long. There's just, I have to kind of front load you with this information. Cosine's going to go faster because a lot of it's the same. Okay, let's look at cosine. So our function is y equals the cosine of x, or in function notation, f of theta equals cosine of theta. There could be parentheses or not parentheses. It means the same thing. Okay, cosine. If we look at our cosine function instead of sine, notice pretty similar shape there. But the difference is it doesn't go through the origin. It starts at its maximum. So 0, 1 is our point here. Negative pi over 2 is at 0. Pi over 2, 0. Pi is -1. And 3 pi over 2 is back at 0. Let's see here, throw a couple extra points in there. We could have gotten all of these just from the graph. Desmos is awesome because it tells you all the maximums and minimums and the x-intercepts, and it makes it really easy to draw these graphs. Cosine, same deal as sine. I can zoom out, and it's going to look exactly the same. It keeps repeating. It never stops. All those little dots are distracting. There we go. Okay, the pattern just keeps repeating itself. So cosine has the same domain. All real numbers, -infinity to +infinity. The range, the same. -1 is less than or equal to y, less than 1, or in interval notation, -1 to +1. It's also continuous. Now, is it also odd? Look at the symmetry. Does the y-axis cut it in half and the left side is the reflection of the right side? Yes. So this one, cosine, is even. Sine is odd, cosine is even. All right, local maximums and minimums. Same deal. There are infinitely many. They just occur in different places. So let's go maximums. We've got a maximum at 0, 1. We've got a maximum at 2 pi 1. We've got a minimum at negative pi negative 1, positive pi negative 1. Again, that's not all of them. That's just what we can see in our snapshot here. Increasing, decreasing. This one, in this window that we're looking at, starts by increasing negative pi to 0. Then it decreases from 0 to pi. Then it increases again from pi to 2 pi. Once again, that's not all of the intervals of increasing, decreasing, but it's the ones that we're looking at. X-intercepts, infinitely many again. I'm not going to rewrite that. I'm just going to list the ones that we can see. Negative pi over 2, 0. Positive pi over 2, 0. And 3 pi over 2, 0 are the ones that we can see. The y-intercept, only have one. You're always, if it's a function, you will always only have one y-intercept. But this one's not 0, 0. This one's 0, 1. In behavior, same deal. This one oscillates, bouncing between negative 1 and positive 1, just like sine is. Again, just in different places. Okay. See, I told you that would go faster. All right, period and cycle length. Let's look at it the exact same way. Okay, starting point is 0, 1 this time. So if we go all the way through one complete cycle and it starts over, that changing point, I guess, is 2 pi. So what's the length from 0 to 2 pi? It's 2 pi. So the standard period is the same for sine and cosine. The standard is 2 pi. Again, it just looks a little different, but the length is still the same. Midline, what runs right through the middle, same deal. The standard is y equals 0, or the x-axis. And the amplitude, same thing. The standard is 1. From the middle to the max, from the middle to the min, for both of those, it's 1. So, last thing we need to talk about today is what makes them not have the standard. What conditions cause them to be a little bit different?